My name is Philipp, and I will tell you a little bit about the experience we gained by looking for Sybils in the Tor network over the last 1-2 years. If you had a look at the list of accepted papers, you could already tell that, I'm having troubles with the slides, I'm sorry. Sorry. Yeah, you could already tell that this was a paper about Sybil attacks simply by looking at the author list, because we somehow managed to get my name on there twice, but USENIX was very quick to fix that, so that doesn't work anymore. But on a more serious note, why are we working on this in the first place? Tor the code is developed by the Tor project, but the network is run by volunteers, the network of approximately 7,000 relays that we have these days. And a lot of these operators, a lot of these volunteers are anonymous. So 30% of these 7,000 relays do not have any contact information. So it's not possible for us to get in touch with any of them. And that is good to some degree, right? Just like we should be anonymous when using Tor, it should be possible to set up a relay that way. So the barrier of entry is pretty low. You can set up a relay in a matter of just minutes, which is good for adoption, because otherwise we wouldn't have that many relays these days. But it also means that it's easier to start attacks. And the attack we're interested in here is called a Sybil attack. So to refresh your memory, a Sybil attack takes place when one person or one entity is running a lot of relays in a Tor network. And this is not just an academic threat. It is something that even the tech press has written about a couple times. So I think many of you might have known about the attack CMU's SCI, the branch, was launching against Tor users a couple months ago. So it's a real threat, which is why we have been working on that. And you might be thinking there is a lot of defenses out there already to defend against Sybil attacks, but in our experience, they don't perfectly apply to the Tor network. So there is a lot of work out there on social network-based defenses, but it doesn't work very well here because there is no trust relationship between those 7,000 Tor relays. There is no concept of befriending a relay. Similarly, proof-of-work systems also don't work quite well because, in a way, proof-of-works are already inherent to running a relay because you're constantly consuming bandwidth, you're constantly consuming CPU power. It also doesn't work that well. So instead, we're leveraging two observations that we made over the course of this work. Number one is that Sybils often are controlled similarly. What I mean by that is that an attacker who runs, say, 10 relays tends to start and stop their Sybils at the same time, for example, to install an operating system upgrade. Similarly, Sybils tends to look very similar if you look at the configuration of these Tor relays. So I have an example here. Every row represents a relay, and every column is basically an attribute. And these are the Sybils that were run by CMU's SEI Institute. And you can see by just eyeballing the rows that they're very similar. The nickname is identical. The IP addresses are from the same /16 network. So they look very similar, right, by just eyeballing it. To really set out and look for Sybils, we are having two data sets. The first one we call our passive data set. And this was already out there waiting for us because the Tor project is archiving lots and lots of data, which is all online at collector.torproject.org. For some reason, it's not used a lot in research, which is a pity because it's data dating back almost a decade. In particular, we're interested in network consensuses. So a network consensus is produced by the Tor network each hour. So each hour we get a consensus, which is basically a list of all running relays, a list counting approximately 7,000 relays. So we use these consensuses that were published each hour over the last 10 years, which amounts to approximately 100 gigabytes of data, which is really cool because it allows us to reconstruct the state of the network for any hour over the last 10 years. The second data set we're using is basically the reason we started to work on this project in the first place. We call it the active data set. This is basically the output of the exit map scanner, which we developed in some previous work. Exit map is a small Python tool that allows you to run a network task over each of the 1,000 exit relays of the Tor network. We use it to find malicious exit relays. So the idea is you send some decoy traffic to a website, you record the response, and then you see if the response is what you would actually expect to come from the exit relay. If it's not the same, then you have some reason to believe that something bad happened, like a man-in-the-middle attack. And we wrote a bunch of new modules on top of the ones we already had and ran them for around 18 months. And that way we ended up with around 250 malicious exit relays. And the reason we started to work on this particular project is because we noticed among these 250 relays, a lot of them turn out to be Sybils, not isolated incidents of maliciousness that sometimes happens in the Tor network, but really systematic attacks by people that occurred one after each other. Of course, there were also some isolated incidents, but the bulk of these 250 relays were indeed related. Having these two data sets, we then developed a new tool that we call sybilhunter. It is free software available online already, and it basically, as you can see on the bottom right, takes as input all the consensuses and then runs analysis modules on them, and it outputs CSV files and images. So far, we have developed 4 different analysis modules that I will quickly discuss before I will dive into the results. So number 1 is, we call it visualizing uptimes, or I also like to call it uptime art, as you will see in a minute. So recall that each hour we get a new consensus. This means that for any given relay, we can determine basically a binary uptime sequence. So you see here 6 hours, and for each hour for a relay, we can say the relay is either online, which means that it's part of the consensus, or it's offline, which means that we can't find it in there. And it turns out that we can do that not only for one single relay, we can do it for many relays, which means that it looks like that. So we basically get a 2-dimensional matrix. And the problem here is, in this particular matrix, we already have 2 relays that look very similar. So the observation here is relays that have an identical or highly correlated uptime sequence are likely to be Sybils. That is not always the case, but it's surprisingly often the case. In that case, it's these 2, right? But it's not immediately obvious because those 2 columns aren't grouped next to each other. So it's very important to sort these columns in a way that by just eyeballing it, you can immediately tell, oh, there are a bunch of relays that have a highly correlated uptime sequence. So we use single linkage clustering for that purpose. And once you apply it to the matrix, it becomes a little bit easier, right? They're now adjacent, which makes it easier to spot them. And not only can we group them next to each other, we can also correlate uptime sequences that have perfect correlation, basically. And again, this is really for visual inspection. You basically look at an image, as you will see in a minute, and it will make it much easier to spot these Sybils. So this is just a small toy example, but let's take a step back and look at these uptime images for the Tor network as a whole. And it starts to look like this. So what you see here is the same thing, just on a larger scale. Again, on the y-axis, we basically have time. Each hour is a consensus. And on the x-axis, we have the relay index. And here we're looking at around 2,000 relays back in July 2014. And there are 2 suspiciously large red blocks here that you can see. And these turn out to be the relays that CMU's SCI was running back then. The big block on the left here was the block that was removed by the Tor project once they learned about the attack. And there is a slightly smaller block that was also run by the SCI that, as far as I know, was not removed, perhaps because SCI stopped it by themselves just a couple hours before the other one was removed. And we generated these uptime images for each month dating back to, I think, 2007, and a gallery of all these images available online if you're curious. But let's have a look at a couple more examples. What we have here is around 1,600 relays in June 2010. And here, somebody was starting around 500 relays on Planet Lab to learn more about Tor's scalability effects. And again, we have, it's pretty obvious here. It's this big red rectangle, right? It works very well in these cases. This is July 2012, and what we had here, so for each case we did some manual analysis to figure out what was going on, and this is approximately 100 relays that originated from Russia and Germany. So each day they came online for a couple hours, and then they were offline for the rest of the day, only for the same pattern to repeat the subsequent day. In this particular case, we're not sure what was going on, but the Sybils we're talking about are not always malicious, right? Some of them are, but some of them are perfectly benign and are really just an effect of volunteers forgetting to express in their configuration files that they're running, basically Sybils. So they don't have to be malicious per se. And our coloring scheme doesn't always work perfectly well. So in this case, you see this bar on the left, which looks like Sybils, but they weren't colored in red simply because the uptimes weren't perfectly correlated. And we can reduce the sensitivity of our algorithm, but we would drown in false positives. But then again, it's mostly for visual inspection, so it's not a huge issue in this case. And this method to visualize the uptime of relays turns out to work very well to look at relays. So it paints a very fine-grained picture, but it doesn't work quite that well on a more aggregate view, right? So if you're trying to figure out what happens between two subsequent consensuses, this is not the perfect way to look at this phenomenon. So for that, we came up with a second method that we call network churn. And as the name suggests, it determines the churn value between two subsequent consensuses. So it paints a more aggregate picture. And the churn is basically the fraction of new relays and the fraction of relays that disappeared from one consensus to the next one. And what we end up with is basically a time series like the one you can see at the bottom right. We see the value exhibiting a really weird zigzag pattern between Monday and Tuesday. And this is an artifact of a research project that took place in 2013, and I'm going to talk about that in a minute. Not only can this sometimes point us to Sybils in the Tor network, it also teaches us a little bit about the network as a whole. For example, we learned that the churn, the median churn, decreased over the years from 0.04 in 2008 to 0.02. So I interpret this as the network as a whole becoming more mature and more stable over the years. But again, in this diagram, we see these Sybil relays that were used in a research project. And this is an interesting way to look at it, but we found that there is a better way to look at this particular issue. To understand how it works, let me quickly tell you about the fingerprint of Tor relays. So each Tor relay has a fingerprint, which is the hash over its public key. As a result, it's supposed to be unique, right? Each relay has a unique fingerprint, and they're not supposed to change because the public relay is long-lived. If it changes once or twice, it wouldn't raise any eyebrows, but if it does so frequently and systematically, it certainly would raise eyebrows. So what we did to find that sort of issue, we added a new method to our tool sybilhunter. And this sort of issue is often a symptom of an attempt to manipulate the distributed hash table that is used to power Tor's hidden services. So for each relay identified by its IP address, we basically keep track of the number of fingerprints we see. And what you see here is the same research project from the previous slide, looked at it a little bit differently. So we see a bunch of IP addresses in a related network space that changed their address, their fingerprint, exactly 24 times. And we tracked it down, and we found out that this was an experiment of the Security and Privacy 2013 paper, Trawling for Tor Hidden Services. So we contacted the authors, and they could verify that this was indeed part of their research project. Let's move on to the final method, which we call nearest neighbor ranking. And it's a little bit different from the previous methods because it doesn't find Sybils on its own. Instead, it's a technique that assists us in analyzing Sybils. Why is this useful? Often when we found malicious exit relays that were Sybils, presumably, we weren't completely sure if there might be more relays out there that are up to the same attack, but that we didn't find for one reason or another. So what we really wanted was a technique that takes as input a Tor relay and gives us a list of the most similar relays according to their configuration, for example. And our current technique is pretty simple. So we take a seed relay and we turn it into a textual representation, which is really just things like the nickname, the IP address, and so on. We do this also for all the other relays that are in the consensus, and then we determine the Levenshtein distance between the seed relay and all the remaining relays in the consensus. The Levenshtein distance gives you the number of basically modifications you need to turn one string into another string. So I have a small example here where it takes 6 modifications to turn S1 into S2. And the smaller the distance, the more similar we see relays. So what does it look like in practice? Like this. We wrote a small tool that is available online. And what we have here is a relay that we run at our university on the very first line, and the subsequent lines are relays that are the most similar to the seed relay. And you also see the distance. The most similar one happens to be another relay that we also run at the same university, which isn't particularly surprising because we went out of our way to basically make the configuration look similar. So this example works very much in our favor, but I think you get the idea of how it works. Let's move on to the results. We ended up with a lot of Sybil groups. Not all of them are malicious, and it takes a little bit of work to analyze them and to figure out what they're up to. In our paper, we focus on 20 Sybil groups that we characterize, and this is really just the lower bound. It's important to understand that there are probably many more out there that we didn't find. We grouped them into 5 categories. Number 1 is man in the middle. So these relays were basically trying to steal bitcoins, and I'm going to talk about that in a while. Number 2 is botnets. So we had 2 Sybil groups that we assume were part of a botnet. We had one group that was basically an attempt to run a denial of service against attack against Tor, not very successfully. We had 4 groups that were parts of research projects, and 6 we couldn't quite classify simply because we didn't know what they were up to. I want to tell you a little bit about the Bitcoin Sybils, because I think this is the most interesting Sybil group we found. So these were all exit relays, meaning that they were exposed to the traffic of Tor users. And their goal was, as we believe, to steal Bitcoins, basically. And the way they did that was to manipulate the HTML code on websites. So you can see 2 sites here, the original one at the top and the fake impersonation site at the bottom. And the only difference is a tiny string, which you cannot really see, it doesn't matter, at the bottom, which is a Bitcoin donation address. And these exit relays would rewrite them transparently. They would recognize Bitcoin addresses and turn them into their own ones in an attempt probably to hijack Bitcoin donations. Not only did they do that, but I think they would also create their own Bitcoin addresses that resembled the original ones. So you can see that some characters looked similar to the original one, probably to fool people that at least tried to verify the first couple digits. And every time we discovered one of those groups, we reported them to the Tor project. They blocked it, but they would show up very quickly afterwards. So we basically got involved in this game of whack-a-mole that lasted for a couple months and might still be going on even. But this attack was financially motivated. So it's a good example of a highly sophisticated attacker, which is quite different from a lot of other Sybil groups we discovered. So what are the limitations of our work? Some of them are already touched on. determining the intent of Sybil groups is often really hard. So we try to figure out why are they online, what are they trying to do. Sometimes it's very obvious, sometimes there is really no clue at all that we can make use of. So this is really difficult, and it involves sometimes a lot of manual analysis. Again, our results are really just the lower bound. There are probably many more Sybils out there, and in our work, we mostly focused on attacks that took place sometimes several years ago. So in an online setting, things are quite different, right? If you consider an attacker that looks at our techniques and that can adapt, it's much harder to defend against that sort of thing. We thought a lot about how to deal with that. There is one way that seems to help somewhat. We found that it can be useful to have an open analysis framework to publish the code, how it works, to make it easier to reproduce our work, but to keep secret some of the specific parameters and thresholds we use, right? And some of you now might think this sounds suspiciously similar to security through obscurity. It's partially correct, but we don't really advocate for only obscurity. Instead, we're advocating for obscurity on top of a more or less sound framework already. And it's also really hard to detect or defend against future attacks, right? So the attack that CMU's SCI division was using was not fully expected. So it was not entirely novel, but it was not something anyone was actively looking for. And of course, there are probably many more attacks out there that we don't quite yet know what to look for. So our solution to that is to have a modular framework that is easy to extend and to make manual analysis as easy as possible so it's easy for us to react. So to sum up, in a way, we're exploiting the laziness of our attackers, right? They're trying to make it easy to control their relays in parallel, and they're also copy and pasting configuration files simply because they want to save time. And we also think that because of the wide variety of Sybils, it's important to have complementary analysis methods. So sybilhunter by itself is not able to detect all these attacks, which is why we're running it in parallel with our exit map scanner. And it's also going to be important to add a bunch of new detection methods as we move on. Another thing is one of our lessons learned that academic research is not by definition always harmless. So you might already have heard that the Tor project is now running a research safety board, which is a great point of contact to talk to before you do your Tor research. It is not meant to police research. Instead, it's really just there to help you do the right thing. We also believe that some of our methods could be of use to other anonymity networks. I had a quick chat with the I2P developers, and they signaled some interest in basically methods to detect DHT manipulation attempts. And we also found it really useful to do some crowdsourcing. So we worked with the Tor project to set up a mailing list that is used to basically have people send reports of relays that sound suspicious. That worked well and not so well. It worked not so well when we exposed it wildly because you get a lot of reports from tinfoil hat people that see attacks on every corner of the network. But once we made it a little bit less exposed, it worked much better when you actually get reports from people who know very well what they're talking about. Okay, so there is a list of people I would like to thank. Most importantly, my co-authors, Roya, Karsten, and Nick. We tried to publish basically everything we did on our project website, anonymity.ch sybilhunting, to make it easy to replicate our work. Finally, and perhaps most importantly, like Pratik already said, Roya is looking for a faculty position. She has done a lot of really great work on networking and measurement, so you should hire her before someone else does. Thanks a lot.
We have time for questions.
Rob Jansen, NRL. Thanks, Phil, for the nice talk. So it's my understanding that you're looking at Sybil relays, right? I'm wondering if you've thought at all about how to detect client Sybils.
Client Sybils as in perhaps botnets, maybe?
Yeah, just an attacker who's using different Tor clients and maybe launching a denial of service attack or something like that?
Yeah, we have not at all, actually, but that's an interesting point. Yeah, I wonder if we could recycle some of our techniques to do that.
All right, well, the audience thinks of a few more questions. I'm curious to pick your brain on how adversaries might respond to sybilhunter now that your tool is published. So you talked about having some secret parameters in the system, but if the output of the system has can lead to publicly distinguishable changes, to what extent could an adversary infer the secret parameters?
Right, that is another problem. So a live setting is really problematic. Like you said, all we are doing is basically to drive up the cost of an attack. And it is certainly possible through a lot of experimenting to figure out what the thresholds are. But then again, it requires cost, which we're driving as high up as possible. But ultimately, through the very nature of Sybil attacks, there is just, we don't really see, given the current design of the Tor network, a fundamental fix to that.
Hi, Trevor Pottinger here. So I really enjoyed the Levenstein distance, the configuration comparison stuff that you guys worked on. Did you guys play around with other sort of encodings of the configuration or alternative distance metrics to try to assess like how similar different things are?
A little bit. So the actual distance metric we use is the correlation coefficient. We played with things like the XOR as distance. I think it didn't make a huge difference. So I'm afraid not an awful lot, but I think there is a massive room for improvement because turning a relay into a simple text string loses an awful lot of information, like the topological nature of IP addresses, port numbers. So this would certainly be a good opportunity for future work.
Cool, thanks.
One more quick question before we let you go. This one is a bit more philosophical in nature. I'm curious, that your current defenses are a bit more reactive in the spirit, that the attack has already happened, and especially since some of the features have to look at historical time series data of relays availability, the impact of the attack could already have taken place, especially for attacks such as Bitcoin stealing. Could you comment on how in the future the Tor network could deploy proactive defenses against Sybil attacks?
So I can tell you the way it currently works. The moment we find out about an attack, we report it to the network, and the Tor network has the ability to block relays by basically having a threshold voting scheme. So the operators of the directory authorities, basically the gatekeepers of the network, express in their configuration file that they want a certain relay to disappear. So we basically send an email to them, they update their configuration file, and this works more or less well. And in a couple of hours, we usually have success in removing a relay from the network. So this has been streamlined to a degree that it works reasonably well, but there is always room for improvement.
Thanks, Philipp.